Hello everyone. This video introduces the Ameba chip-in module. Chip-in stands for Chip Enable. As its name implies, it's used to control system resets. This video will cover the following topics. First, we'll start with an overview. Next, we'll introduce the Debounce function. Then, we will explain its three working modes: level reset, interrupt reset, and pause reset. Finally, we'll demonstrate how to program this module with practical examples. First, the chip-in module supports three working modes. They are level reset, which is the default working mode. Then there are interrupt reset and pause reset. Regarding the Debounce function, we provide a wide programmable range. This range spans from 0 microseconds to 16 milliseconds. By default, it operates with a debounce time of 100 microseconds. This function is effective for all three working modes. Next, let's talk about the power-on sequence. For the power-on sequence, please be sure to refer to the chip-in reset sequence chapter in the datasheet. All three working modes are required to follow this power-on sequence. Now, let's discuss the Debounce function. The hardware only detects a continuous low level, or a continuous high level signal, when its duration exceeds the configured debounce time threshold. Only then will the hardware recognize it as a valid, low level or high level signal. The hardware does not respond immediately after detecting a signal transition. Only after the debounce time has passed will the hardware register the signal change. Signal changes with a duration shorter than the set threshold are automatically ignored by the hardware circuit. The signal processed by the Debounce module is then passed to the next stage, which is the circuitry for the three working modes we mentioned earlier. Furthermore, all subsequent timing functions are based on the signal processed by the Debounce module. Regarding the working modes, let's start with level reset. Level reset is the circuit's default working mode. When the signal is low, the chip remains in a reset state. It's not until the signal goes high that the chip will start up. Its typical application scenario is when there is no user button input. It's also used when no other host controller manages the Ameba's startup. Its main characteristic is its simple logic, and it is the chip's default working mode. Next, let's introduce interrupt reset. Its practical application is similar to a mobile phone's power button. With a short press, you can turn the screen off or on. With a long press, if the system is normal, the phone shows a menu asking if you want to reboot or enable airplane mode. If the system is unresponsive, the phone reboots directly. For this scenario, we can implement it using the interrupt reset function. The user needs to program three time-related thresholds: SP for short press, LP for long press, and AC. When the low-level input signal reaches the SP threshold, the module will generate an interrupt. At this point, we can use this SP interrupt to make the system enter a low power mode, or to wake the system up. This is similar to short pressing the power button on a phone to turn the screen off or on. When the low-level signal's duration reaches SP plus LP, at this point, an LP interrupt is generated. If the system is working normally, and within this ACK time window, the application responds in time by clearing the LP interrupt and handling the ACK event. Then the module will treat the LP interrupt as a regular interrupt. However, if the system is abnormal, and within the ACK window, the application layer fails to respond and clear the LP interrupt, then once the ACK time is reached, the module will enter a reset state. And when the signal transitions back to high, the system will reboot. It's important to note that, after a reboot, the module reverts to the default level reset mode. If you want to continue using the interrupt reset mode, it must be reconfigured by the software. Next, we'll introduce pause reset. This mode's application is similar to a router's reset button. Pressing the button briefly will cause a reboot. Pressing and holding it will restore factory settings. For this application scenario, you can use the pause reset function. When the input signal transitions to low, it will immediately trigger a reset and reboot. At the same time, the module also provides a function to check the chip-in level status. During the boot flow, the software can continuously poll, waiting for the chip-in level to go from low to high, and measure the duration of the chip-in low-level state. Based on the duration of the press, different actions can be taken. For example, a long press, meaning the low-level duration exceeds a time threshold, can be used to erase user data in the flash and restore factory settings. A short press requires no extra action and is treated simply as a system reset. Unlike interrupt reset, the timing here is done by software, not by hardware. It is important to note that, once configured in pause reset mode, the software cannot change this working mode. Only a power cycle can make the chip-in module revert to the default level reset mode. Next, let's look at the chip-in module application examples in the SDK to briefly introduce the main APIs, their functions, and how to use them. The example is located in the SDK's root directory, under component example peripheral raw reset. This directory provides two application examples: interrupt reset and pause reset. First, let's look at interrupt reset. These are some time-related parameter settings. The first API sets the debounce time. The second API sets the short press and long press thresholds. The third API sets the acknowledgement window. Next, using chip-in work mode, you can configure its working mode to be interrupt reset, pause reset, or the default level reset mode. When using the wake up and low power functions, we can register the wake up source in two ways. One way is to call the API directly. The other way is to modify wake up null inside sleep event config, changing it to wake up km4 or wake up kmning. If you are using another IC, you can refer to the name of the corresponding CPU to be woken up. You can choose either of these two methods. Then, the next step is to register the interrupt handler. In the interrupt handler, you can choose whether or not to clear the LP interrupt in a timely manner. This was a brief introduction to the interrupt reset example. Now, let's look at pause reset. Pause reset initially operates in level reset mode. If we want to configure it as pause reset, we can first set the debounce time, and then configure its working mode to pause reset. When it's already in pause reset mode, and a reset event occurs, causing a reboot, we can then get the current status of the input signal to check if it's in a pressed or released state. When it is in the pressed state, we can have the task block here. When it is released, the execution will continue. At this point, we can get the elapsed press duration. This duration can be compared with our set threshold to distinguish between a short press and a long press. This threshold could be set to, for example, 5 seconds. That concludes the introduction to the two examples. If you are interested in more specific details about the chip-in module, you can refer to our online documentation. This has been the introduction to the chip-in module. Thank you.